Um, Here again is the summary of the Kalman filter from the system model, and then how do we propagate and update our estimates of the state vector x. And recall if this process noise was zero, meaning this Q was zero, the Kalman filter gives you the weighted least squares solution recursively. Normally, this stuff is done in a computer. Real-time applications like vehicle tracking of vehicle or navigation. Where are we and how are we oriented? I went through a few examples of smaller problems that could be done by hand, so you kind of know how these equations work. I did that in the previous video. But I want to get to a couple of leftover things, and then we're done with the Kalman filter itself. The next module will be the extended Kalman filter, which is a linearized version. But let me wrap up a couple of topics for just the Kalman filter. We kind of glossed over initialization. How do you start this filter? What is your very first estimate of the state and your covariance here, or your error covariance? And there's two ways to go about it. One way is to use your measurements, your first or early measurements, to build up an initial estimate. The other way is, I could call it guessing, but you should know something about your situation. And for the simple scalar problem, here's some example arithmetic. If you remember that problem, we're just getting measurements of an unknown quantity. From the very first measurement, you could just say, well, my first estimate is that first measurement, and my first variance on the error of that estimate is just the measurement error. That makes total sense. And it's kind of nice when you're just working with scalar. But you could have a bigger state than you have a measurement. You're not going to be able to reconstruct a whole state on a single measurement. It might take you 2, 3, or more to get enough to where you can algebraically construct a whole initial state estimate. So you would have to kind of wait around and not actually go through the filter until you've processed several individual measurements to the point where you can construct the whole state vector estimate. So anyway, this was a simple case for a scalar case. If you start out with the guess, start out with a sort of pre-estimate of your state and a pre-estimate of your error covariance. But you choose a big enough initial error covariance. If your initial error covariance, the one you actually guess at before you get any real measurements, if it is large compared to your measurement error, you'll essentially get, after that first processing that first measurement, you'll get about the same solution as this solution anyway. So I personally like the guessing method. That way you don't have to have sort of separate algebraic solution just to initialize your filter. This is that Bayes estimation controversy. Where did you get these initial guesses before you got any measurements? You could make an argument, like if you're trying to track another airplane with a radar, you know what kind of detection range your radar has. You know, it kind of can put some bounds on where you're probably going to first detect another airplane. It's not like a total guess. If you know something about your radar, anyway, that's just an example where it's just, I use guess in quotation marks because it's not truly a total guess. Anyway, and the second and last little piece of information is if you look at these updating equations, you need to compute the gain and update the error covariance matrix. Those equations do not involve your measurements. You don't need measurements to do these computations. So you can compute them ahead of time. In fact, you can kind of see how accurate your little filter is going to be before you actually get real measurements. That's at least if everything obeys your system model. And if these matrices here are constants, meaning these subscript k's don't really matter, then you can pre-compute them kind of easily. I'm not going to go through this algebra. I just want to get through this kind of fast. But if you go through the algebra of pre-computing them, you get this equation down here, which, yes, it does look terrible. This is the so-called Riccati equation. And MATLAB, for example, has I think it's a one-line command that solves the Riccati equation. So if you get kind of bigger matrices, you can have MATLAB do it. If you have a scalar problem, you can do it by hand. And again, I'm not going to go over the algebra of it, but if it is a scalar problem, the Riccati equation just ends up being a quadratic equation, and you can solve it by hand. And I put this on exams sometimes. Here was an example. Here's your little state model or your system model, process equation, measurement equation, your noise terms. And from there, you can figure out what your phi, q, h, and r are. You put them in that little Riccati equation from the previous chart. You end up solving this quadratic equation, quadratic formula, and at this. And by the way, you need to pick the positive number. You can't have a negative number for a variance. And you get what your steady state gain is going to be and what your steady state error covariance matrices. Here it is before you get an update, and here it is after you get 0.33 after the update, 0.50 before the update. What's going on there is you had this transient phase where the covariances or variances were trending down. Remember, they grow between measurements, and every measurement comes down some. What we just calculated were these two thresholds here. In steady state, the upper value and the lower value. That's what these two numbers are. This is the upper value. This was the lower value. And you could also analyze your system. Analyze your system this way. This predicts, without you actually processing any measurements, how accurate your filter is going to be. And that's it for just Kalman filter.